Welcome to lecture 6.2. Here we'll be expanding on the flexibility method and applying that to structures with multiple degrees of indeterminacy. The goals for this lesson are to start by constructing the compatibility equation for multiple degrees of indeterminacy. This is really where things change in setting up the compatibility equations. Once those equations are set up, we approach it pretty much as we have before, to try to solve for each of the unknown variables. So with that in mind, we'll solve some beams with multiple degrees of indeterminacy, and finally we'll learn about Maxwell's theorem that allows us to reduce the number of unknowns by a few to help us out. So what happens when a structure has more than one degree of indeterminacy? Well, let's look at this by taking a look at this example here. We have a total of 5 reactions, which for a standard beam means that we have a degree of indeterminacy of 2. And so to create our primary structure, we have to remove 2 redundant reactions this time. So thinking about this for a moment, it's clear that we have to remove 2 of the rollers for this to remain stable. So let's look at the possible combinations. The first is treating B and C as redundant. The second possible option would be treating B and D as redundants. And the third possible primary structure would be treating C and D as redundants and removing them. Now again, we want to go with structures that are the most familiar to us, preferably so we can use tables later on. So really, number 1 is the most familiar, although all these structures are relatively easy to solve. So we'll go with 1 for this example. So now let's construct the compatibility conditions based on the primary structure that we've chosen. Based on superposition, the fully restrained structure on the left is going to be equal to a sum of different primary structures loaded in different ways. Let's look at the full structure first. The deflected shape is going to look something like this. Again, this is just a qualitative estimate. Based on our choice of primary structure, our primary reactions would be dy, ay, and ax. These are the ones we'll solve for at the very end using equilibrium conditions. Our redundant reactions would be by and cy. These are the ones that we have to determine using the flexibility method. So we notice that at those restraints, we have conditions that need to be met. The displacement at B has to be 0, and so does the displacement at C. Okay, that is the start of our compatibility equations. Now going over to the right, again, we use superposition of different loadings of the primary structure. We always start with the 0 system, which is our primary structure loaded in the same way as our fully constrained structure. That's going to have a deflected shape that looks roughly like this. And the deflections that we're interested in this 0 system are obviously the ones that line up with the constraints that we want to enforce. So there we have delta B0, and here we have delta C0. Now in order to cancel out those displacements, we need to add 2 more loaded primary structures, 1 for each of the redundant reactions. So the first we'll call the B system, because we'll load that at the B position, and the second one we'll call the C system, because that'll be loaded at C. So let's look at the corresponding deflections of these 2 systems. We know that the B system will deflect a little more at B, and then the C system will deflect a little more at C, but both of them will have displacements at the other points. So that's really the important detail to keep in mind. So whatever force we apply at C still will have an impact on the displacement at B, right? And that's really what changes here when we have multiple degrees of indeterminacy. So let's color code this so it becomes a little easier to follow. We'll call the displacement at B for the B system FBB, and we'll call the displacement at B for the C system FBC. Okay, just a quick note about this notation. Whenever we say FBC, for example, we're referring to the displacement at B due to a force applied at C. Or in other words, the displacement of B for the C system. Recall that I call it the C system because the force is applied at C. Now similarly for point C, I'll call the displacement for the B system FCB, and the displacement at C for the C system FCC. So you'll notice that I'm using unit forces here, right? That's not going to be necessarily enough to cancel out the displacements of the zero system. So we need to scale the results of each of these systems. The B system is going to be scaled by the magnitude of the reaction at B. The C system is going to be scaled by the magnitude of the reaction at C. So I simply denote that by putting the system in brackets and multiplying by the corresponding reactions that we're trying to solve. So notice that By gets multiplied by both BB, FBB, and FCB. Okay, so with that defined, now we can set up our compatibility conditions. So we need two in all, right? One for the displacement at B and one for the displacement at C. Okay, so number one for the displacement at B, we have delta B equal to 0, of course, and that is equal to the sum of all the corresponding terms at B. In fact, I'll go ahead and color code the zero system as well, so it makes sense, right? So we want for delta B, we want the sum of all the green terms. So we have delta B0 plus By times FBB. Remember, right, we have to scale the system, plus Cy times FBC. I'll go ahead and make delta B red as well so it matches the primary structure, right? So we have delta B is the sum of all the green terms, and delta C is going to be equal to 0, and it's going to be equal to the sum of all the purple terms. So there we have our two compatibility equations. Keep in mind that it is the last term in the subscript, right? B and C here that correspond to the force that it is getting multiplied by. So that's just a way to check yourself, make sure that you're not mixing things up. Okay, so we have a system of two equations that we need to solve. Now, of course, you can do that by hand, but these compatibility equations actually lend themselves really easy to linear algebra and solving using matrices. So we can set that up pretty easily, actually. So we can set up a 2x2 matrix of the F terms multiplied by the corresponding reactions, right? So take a moment to verify that if I do the matrix multiplication there, I get the right products. And this 2x2 matrix of the F terms is what we'll call the flexibility matrix. And completing the equations, right, we can say this gets added to another 2x2 matrix of delta B0 and delta C0, and that's equal to 0. Okay, or rearranging this, right, moving the big delta matrix to the right side, we get a better form of this equation, which is the flexibility matrix times reactions is equal to negative delta matrix. Okay, this is pretty much in standard linear system format, which means we can apply rules of linear algebra here to solve it. So essentially all we need to do is divide by the flexibility matrix, multiply it by our deltas to get our by and cy, which is really what our unknowns are once we get to the compatibility conditions, right? So by and cy, that matrix or that vector is equal to negative the inverse of the flexibility matrix times our delta vector, okay? And this is an operation you can do pretty easily in a scientific calculator or in MATLAB to solve. So this would be the last step. We still need to actually go through either principle of virtual work or using tables to actually get the F terms and the delta terms. But this is multiple indeterminacy using the flexibility method in a nutshell. So you can use, essentially, you can use this slide as kind of a cheat sheet to get you through most of these problems. So let's go through one example. All right, we have a left-hand cantilever beam here supported by 2 rollers. Again, 5 reactions, so our degree of indeterminacy is 2. And the only loading here is a moment of 450 kilonewton meters around point C. All right, so in terms of possible primary structures, we could have a cantilever, we could have a simply supported beam at A and C, or we could remove the roller at C and the moment support at A and have a simply supported beam at A and B. Probably the first two are our better candidates here. Just again, kind of standard structures. I'm going to go with system 1 because I know I have a table for that, but you also have a table for system 2, so you could also take that approach. So let's go ahead and establish the compatibility equations. So again, we'll start with our fully restrained structure here on the left, and it helps to draw the deflected shape. It's going to look something like that, with a straight line out of point A, delta B equal to 0, and delta C equal to 0. Now, you don't have to get this deflected shape right, okay? It's pretty easy to solve this without doing the deflected shape, but it does help, right? The important thing is that you understand what the constraints are, right? That it must be 0 at B and it must be 0 at C. So let's then use superposition here. Let's define our 3 systems. Our 0 system is going to be our primary structure loaded by that end moment, right? That's already defined. Our second system is what we'll call the B system, that we will load at B with a unit force. That'll create a displacement something like that up to 1 and then just a straight line. So we have FBB and FCC. And then for our last system, that would be our C system, because we'll load it at C, again, with a unit force there to correspond to the roller support. And so that'll bend all the way to C. So this should be FBC, and this should be FCC. And I realize I made a mistake labeling over here. That should have been FCB. Displacement at C due to force at B. Okay, now we have our labeling right. Okay, we have to remember that these will be multiplied by the corresponding reaction. Again, good idea to put this in brackets so you understand that they're getting multiplied or they're getting scaled by the reaction. Now the last thing we're missing is the 0 system here. The deflected shape will look something like that. We'll call this delta B0, and we'll call that delta C0. All right, so with those, we can set up our compatibility equations. And we have number 1, we have delta B equal to 0, equal to delta B0 plus By times FBB for the B system, plus Cy times FBC for the C system. And similarly, the second compatibility condition for delta C will be, all right, so the plan of attack here is that we'll solve for delta B0 and delta C0 first. Second, we'll solve for FBB and FBC in the B system, and then FCB and FCC in the C system. Let's start with our zero system. The book likes to call it the release structure because we've released certain constraints. And I've displayed the right table to use here, right? We want a cantilever beam with a moment applied to it. So again, here we want to solve for delta B0 and delta C0. And we can do that using the equations. We just need to make sure our terms are consistent with the table. So for the table, A is going to be equal to the length of the beam, which from here we know is 12 plus 12, so 24 meters. And the moment is going to be equal to 450 kilonewton meters. Rotations match, so we don't need to make that negative. So for delta B0, we'll need to use this equation for x equal to 12. All right, so we get negative mx squared over 2ei. So negative 450 times 12 squared over 2ei. That results in negative 32,400 over ei. Similarly for delta C0, we can use that equation with x equal to 24, or we can use the equation for YB, plugging in A equal to 24. Either one will give us the same result. We get negative ML squared over 2EI. That gives us negative 450 times 24 squared over 2EI, or negative 129,600 over EI. Okay, so simple enough. That's our zero system. Moving on to the B system. Now we have to use a different table, one for a force applied to a cantilever beam. So from observation, we can say that A is equal to 12 meters in this case, because the 1 kilonewton force is applied at the center of the beam, and P will be equal to negative 1 kilonewton, because the force is being applied in the opposite direction as that in the table. So drawing our deflected shape, we are after FBB here and FCB. Okay, solving for FBB first. That is for x equal to A equal to 12, using this equation here, right, for our displacement. And so that gives us negative PA squared over 3EI. Plugging in numbers, we get the following. And then simplifying, we get 576 over EI. For FCB, we can take this equation for x equal to 24, and that gives us the following, and plugging numbers in, we get the following, which simplifies to 1,440 over EI. Moving on to our C system, very similar procedure, only that our force is now at a different location. So force is now applied at A equal to 24. And again, it's in the opposite direction, so we have a -1 kilonewton value. And the positions that we want to solve for are, of course, at B for FBC and FCC. So for FBC, we get the following, where we're using this equation here and plugging in x equal to 12. And plugging in values, this simplifies to 1,440 over EI. And then finally for FCC, plug in x equal to 24 for this equation, or we can just use YB, either one. And plugging numbers in, we get 4,608 over EI. Now we'll make an observation here that FBC is the same as what we got for FCB. In fact, this will always turn out to be true, as we'll see a little bit later on, but we'll just make that observation now. So in summary, we have delta B, delta C, and all the F values. And so we can plug that into the compatibility equations and solve for BY and CY. And I'll do that using the matrix method I showed you earlier. So we have the vector BY, CY equal to negative the inverse of the flexibility matrix. Notice that by virtue of the values for FBC and FCB being equal, this matrix is symmetric. This will always be true as well. So the matrix will always be symmetric. That's a good way to check that you've done things right as well. And this gets multiplied by the vector of delta B and delta C. Notice that the values in that vector are both negative, according to what we've got here and here, so important to keep those signs. And then solving this equation, we would get another vector which would represent our two reaction forces. So notice that BY is equal to negative 64.3, meaning that we guessed the direction incorrectly, right? So we pointed our force up in the B system here, when in fact the true direction is down. And the force for CY is positive, meaning that we pointed the reaction up here, and that is the correct direction. Okay, so in summary, BY is about 64 kilonewtons down, and CY is about 48 kilonewtons up. So this observation that FBC and FCB are equal is explained by Maxwell's theorem. The theorem states that for a linear elastic structure, the deflection at a point A due to a unit load applied at B is equal to the deflection at B when a unit load is applied at A. Okay, so let's look at that graphically. All right, so let's say we have two systems of the same structure, simply supported beam in this case, and we just pick two arbitrary points on this structure, which we call A and B. Now for system 1, I'm going to apply a load at A, a unit load, and for system 2, I'm going to apply a unit load at B. So you could think of these as, an A system and a B system. Those two systems are going to deflect differently, and we're going to measure the deflections at both points for both structures. So using our normal convention, I'll call the deflection at A for system 1 FAA, and the deflection at B FBA. And similarly for system 2, the deflection at A will be FAB, and the deflection at B will be FBB. Okay, so Maxwell's theorem states very simply that FAB and FBA will be equal, regardless of where those arbitrary points are. Now, this is all you need to keep in mind. And this is what actually helps us in the long run because we need to calculate only one of these points to know the other one. So it saves us, in the case of 2 degrees of indeterminacy, it saves us one calculation. Okay, with greater degrees of indeterminacy, it'll save you additional calculations. So this is all you need to really know. But if you want an explanation for why this is true, all we really need to do is think about principle of virtual work applied to both of these systems. So let's say I'm going to apply principle of virtual work for system 1 to calculate FBA. In this case, I would choose 1 as my real system and 2 as my virtual system. Therefore, my corresponding virtual work equation would be 1 times FBA equal to the integral over the entire beam. We won't worry about sections here. Let's just pretend it's the integral over the entire beam of the moment from my real system, which I'll call M1, times the moment from my virtual system, which I'll call M2, over EI dx. Okay? So again, this is real, this is virtual. Okay? So now you can probably see what's going to happen. If I want to solve for FAB in the second system, then my situation flips. My real system is system 2, and my virtual system is system 1. So my equation becomes 1 times FAB equal to the integral of my real moment M2 times my virtual moment M1 over EI over dx. Right? But all we've done is flip the product, which of course doesn't change anything. So the equations for FBA and FAB are identical. And so those values must be equal to each other. So therefore, FAB and FBA must be equal. Okay. Now I won't ask you to prove this at any point. All you really need to know is that statement and that relationship, and you can apply it to save you work in some of these problems, right? So the way that we solved the problem before really took an extra step that we didn't need to, right? We could have avoided calculating FBC for the C system, for example. So this is just simply kind of a background information for you to understand where this theorem comes from, and to realize that principle of virtual work is a powerful tool not only for solving for deflections, but also presenting some of these theorems. So in summary, we looked at analysis of structures for multiple degrees of indeterminacy, and we used the flexibility matrix in this case to solve for 2 or possibly more compatibility equations. But otherwise, the procedure is fairly similar. We just need to keep in mind that once we have more than one redundant reaction, the reactions do have combined effects, coupled effects. So each of one affects the other, right? So they all need to be taken into account in the compatibility equations. And then we also learned that Maxwell's theorem is a nice convenient property for these systems of multiple indeterminacy, and you can use that to save you some work. The thing to note is that the number of unknown deflections, right, the elements in the flexibility matrix, as well as your deflections for your zero system, do increase exponentially with additional degrees of indeterminacy. So for 3, now you have to solve for a total of 9 unknown displacements, even if you're using Maxwell's theorem to save you computation. So it gets progressively harder, so not a great tool for anything probably over 2 or 3, unless you want to do a ton of work. Okay? And of course, tables also help a lot here, right? So we will be using tables extensively for multiple degrees of indeterminacy, especially because, again, doing principal virtual work would entail even more work. So always try to set it up such that you can solve these problems using tables.